here. Cancel. Here's a data sheet. So a lot of times you're asking, hey, if I just learn one type of microcontroller in this class, would I be able to use all different kinds of microcontrollers in the future? The answer is yes. So before this class, I actually only had like 1 or 2 experience with the Atmega 2560 microcontroller in the past. So the one I taught at Mines was the PIC 18F or something. But eventually, the timers and how to handle the timers and interrupts are just super similar to each other. For this one, if you click, you can search all different kinds of controllers and registers and resources inside the chip. So if I type TCCR1B, I'm pretty sure you don't know what that is. It's on the exercise, actually. Now here's the answer, right? So what is TCCR1B, and why do we need it? It's actually really simple. So the microcontroller is a digital chip. It's like a user menu, right? So you can look at the menu and see how things are working, and you can modify the controllers. But for consumer electronics, usually they will give you a remote, right? So then you push the button on the remote to change the channels and change the settings, right? But here is a very similar concept. You change the settings of the microcontroller by modify the bits in the registers. Okay, this is one of the reasons we want to use registers. Otherwise, how do we change the settings? Are you expecting using the remote? Right, it's too time consuming. So as a programmer, we can actually modify. There are hundreds of settings of registers you can modify, and you toggle one or several bits in these registers, and you can change the operating mode of the microcontroller to a totally different one. For example, TCCR1B, it is called timer counter. So TC is a timer counter controller. TCC is a timer counter controller register. 1. Why is it 1? Because there are several timers. Timer 0 to timer 5, I think. So there are 5 timers. Okay? If you buy a cheaper microcontroller like the Arduino Uno board, which is a Atmega 328, only 28 pins, right? So there are probably only 3 timers. So why 5 timers is better than 3 timers? Okay? Sometimes you want to modify, you want to have some nested interrupts. We'll cover what interrupts are, but you want to handle multiple tasks at the same time. And you are using some of the functions, libraries online, right? You just download a library and you want to use it, but that library is running behind the scenes, is taking timer 0 or timer 1, and now you want to you do need another 2 timers for your code, and you're just running out of timers. So it's better to have more timers. That's why this chip is more expensive, like $17. But the 328 for Arduino Uno board is only like 70 cents per chip, and this is like $17 per chip. So if you look at this register, it's a timer counter controller register for timer 1. Okay, how many timers do you have? Let's take 5. If I remember that correctly, let's take a look at it. How many timers do we have over here? I have a note here. Timer 0, timer 2, timer 1, 3, 4, 5. Timer 0 and timer 2 are 8-bit timers, and timer 1, 3, 4, 5 are 16-bit timers. So the difference is that for 8-bit timer, the timer has a little counter, and the counter is counting at a certain frequency. If it's an 8-bit timer, it counts up to 255 and it overflows. If it's a 16-bit timer, it times up to 2 to the 16th, right? I think it's a 65. Let's calculate it. That's a useful number here. 16 bits, right? 65536. it counts up to this. So which means it's all the 16 bits are all ones, right? All ones, and then this is the decimal number for that final count. So the benefit of using a 16-bit counter is that imagine that you are using a timer. So timer, you can imagine could be a very similar functionality as the timer you set up in the kitchen, right? You set up a time, and whenever the timer is up, it overflows in microcontrollers and it beeps in the kitchen. It's a very similar stuff. So you can, measure the timing accurately with all these different timers. So there are several different ways of calculations. Okay. So for example, a certain you want to play a music note for a certain duration, and you have to use a timer to accurately control the timing. But how do we do that? Let's take a look at the final result first. This is given, okay? Task 1 is given. So you directly upload the code to the board. If the board is working, you should be able to hear this.
If you load the example code from the website to the board, and here's the top button, and you should hear this. Here's the bottom button.
The different tones is basically a different frequency of oscillations, and when you press it, you can see that if I press it, it plays. If I release it, it stops playing. So which means you can imagine there will be a while loop, right? While it is low, right? And then have a curly bracket having that keep playing within the loop. So with a certain frequency, but how can you control that frequency? That's the question. Because it's playing with a certain tone or pitch that based on the frequency. So if you can either use a time delay, you delay it to a certain amount of time and then toggle. Okay. It's basically like toggling with a certain frequency for a certain pitch, right? After you do this, time delay, toggle, time delay, toggle, time delay, toggle. That's how I handle that. So you can use microsecond time delay. A second method, if you watch the video here.
And you should be able to switch back and forth, and pressing any of the buttons shouldn't disable the other one.
Okay. So the two buttons, the first one is using the first method, which is time delay, microsecond delay, the time delay function you did for tutorial 1. And the bottom button is actually using a timer. So it's a very good way to verify, because the microsecond delay is actually the one we find out from the oscilloscope. Okay, so we assume that it is accurate, and then we use a microcontroller's timer to do the same oscillation, and we hear the same tone, right, or same pitch. That means the microsecond delay function we find out from the oscilloscope is accurate. Maybe there will be a little tiny of differences, but at least your ears cannot figure out the differences. You know what I mean? So there's two different methods, and you can see that if I use the top button to play it, it's actually going through all the notes in the list. It's easy to do. You can directly just write the different notes in the list and going through one by one. Every time you just increment the index, right? You press one time and then increment the index. That's easy to do. But you can probably notify that. You see, if I press the top one,
and you should be able to switch back and forth, and pressing any of the buttons.
Did you notice that if I press the top one, it's going through all the notes on the list, and when it stops, then I start pressing the bottom one. It actually continues from the previous note. It didn't stop and start over. It just continues from that location on the list. Pay attention to that. If I can switch back and forth. So you guys let me know how
shouldn't
can make that.
Board. And here's this.
See? dun dun dun.
Where's the bottom button?
Dun 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 dun.
And you should be able to switch back and forth. And pressing any of the buttons shouldn't disable the other one. Okay.
So it's following that sequence, right? It's not interrupt. It's not stopping that and start over from the list. It's actually continue going from that that note. Do you know what I'm saying? How do we make that work? So actually, it's the index. You just make the index a global variable. All right, just make that index a global variable, right? For the two different functions, the method one is a microsecond delay method, and the second one is a timer, and they share the same index or the same I. So you can keep going from the after the first one, the microsecond delay method, it still keep going from that location. It's not starting over. So fortunately, the code is provided. Before we get into this, I think we should talk about timers. All right. This is what the timer can do, and this is how it works. Let me open up I don't have a copy here, do I? I don't. I expect I'm gonna have a copy because I was expecting someone is not attending class. Everyone is here today, which is good. Let me see. This guy. So assuming a music note is 800 hertz, what does that mean? It has to oscillate at 800 hertz to make that sound, right? Just the oscillation. It could be a square wave oscillation, it could be a sine wave oscillation, nobody cares, because whenever it's going really fast, you couldn't really tell it's a sine wave or a square wave. It's just the oscillations. It doesn't really matter, okay? And it's just an 800 hertz oscillation. So if you inject that oscillation to a speaker, it's gonna make that kind of pitch, okay? A certain frequency will make that pitch. And so what is the period in milliseconds? Oh, it's so easy. 1 over 800 hertz. It's gonna be in seconds, right? And times 1,000 will be in milliseconds. Make sense? So what is a half period? Let's say in milliseconds. Half period.
625?
Yeah, just divide by 2, right? So whatever you got from the first one, divided by 2. And what is the number of timer counts until it toggles the pin that generates this sound? So this will be something new, and that explains how the timer controls the sound. So the way that works is, since the goal is to make an oscillation like this happen, and this need to be 800 hertz. This need to be 800 hertz. Okay. So what's happening is you set up a timer. You start a timer. Like if you zoom in this part, do this. Okay, zoom in. So start a timer here. And timer is up. Okay? So what you can do is you can easily toggle the digital pin by the digital write function. We have done this a lot in the past, right? Digital write. You can either flip it, that digital pin's output, or you can do a reading and then flip it. Remember the function we use? This, right? This. That's how you flip it, how you toggle it. So digital read, you read it from the speaker pin and then you invert it. That's something we can do. So how do we know the timer is up? That's the question, right? So when the timer is up, we can do something, but how do we know the timer is up? So timer is up, you'll start the timer again, and then do the same thing and toggle it, right? So you can keep going and keep going to generate this accurate frequency for oscillation. So how do we know that the timer's up? So first, there's a register. The register's name is timer count. TCNT, timer count. Why timer count 1? Because it's using timer 1. Is timer 1 16-bit or 8-bit? 16. Timer 0 and timer 2 are 8 bits. And timer 1, 3, 4, 5 are 16 bits. So timer count is actually the count holding all the counts in the timer. So there are multiple ways to finish the counting of the timer or signal when the timer is up. But one of the ways that we will use a lot in the semester is just a simple overflow. So keep in mind, this overflow is different from the two's complement overflow. It's just basically it counts all the 16 bits, finish all the 16 bits of counting. So what's happening is, if you look at the timer count 1, so it's actually the timer 1's count register. It's a register that hold two 8 bits. It's TCNT H1 and TCNT L1. So each one has 8 bits. It's basically two 8-bit registers for TCNT1, okay? That's the 16-bit register, but has two 8-bit registers. The reason for that is it's an 8-bit microcontroller, so all the registers are organized in the 8-bit format. So it has a higher 8-bit, lower 8-bit. If you're using timer 0 and timer 2 and looking at the counting, the count register, they probably just has one 8-bit memory bank or register bank over there instead of two, because this is 16 bits. Okay, that's the difference. So let's imagine, okay, because the compiler or the IDE can actually shift, so it's actually running behind the scene. So what's really happening is this is not directly being put at the lower 8-bit. So they grab this register, even though it's 8 bits, it's just holding binary numbers. But whenever it's calculated, it's trying to form this TCNT1 16-bit register. They shift this one to the left by 8 bits, and to make this LSB not 1, but instead of 1, it's actually 2 to the 8th, right? So 1 here is 2 to the 8th. Because there's no difference if you just look at the numbers. The register is a register. Register is just a memory bank in the CPU, right? Or in the microcontroller. There's no difference. However, whenever it forms this one, it's running behind the scene, it compiles it, it knows what's really happening. So it's actually shifting this one to the left by 8 bits, and then OR this guy to it, right? So you are forming a 16-bit counting number instead of 8 to 8 to 8-bit memory banks. You know what I mean? Okay. So now let's imagine there's a TCNT1, right? 16 bits. Keep in mind, this thing doesn't exist. This thing doesn't exist. So this register is formed by treating this bit 2 to the 8th instead of 1 LSB, because it's being shifted to the left by 8 bits. Okay? But now let's imagine this thing is already formed, right? By shifting this one to the left by 8 bits, and then OR this guy. So you are getting this here and this here, okay? So you are forming a 16-bit register. Can you imagine? Because it's being used that way. It's being used that way, even though it doesn't physically exist. Okay, so now this one can start counting from all zeros until like all ones, right? All ones. From 0 to all ones. So how many numbers are being counted in there? How many numbers? 2 to the 16th. So what's the maximum number we can get in this memory bank? Right? That's the maximum number. And that's the number of counts. Does that make sense? This is fundamentals. Make sure you guys can answer this at least, right? This is can happen in the interview. You have to know this. Any question on this before? I'm pretty sure there are multiple people don't know, but feel free to ask any questions you may have.
So what did we get for the period? What did we get for the period?
We'll get it for the period.
Yeah.
We're not there yet, but now just talking about the register, okay? Yeah.
Why is it 2 to the power 16 minus 1?
Yeah, because it's like the 255, right? 255 for 8 bits. 255 is 2 to the 8th minus 1, right? 2 to the 8th is 256 minus 1 will be the maximum number. It's counting from 0 to that number. So total you got 256. Yeah, this is 0. Because this 0 is which 0? This 0? Which 0? This 0, right? Where is this guy? It's here. How many bits following this guy? How many bits following this guy? 8. 8. So this is being put here, and this one is being placed here. That's why this single bit here, or the LSB of this register, represents 1. Which is wrong. So one single bit here represents what? 2 to the 8th. Make sense? Okay. So which is this guy? Because there are 8 ones, 8 bits here. So that's why this guy represents 2 to the 8th. Okay. What about this bit? The 17th bit here. This guy represents what? 2 to the what? 2 to the 16th. Since you have 16 bits following it, that's why this single one here is 2 to the 16th. This guy is 2 to the 16th. Right? It's very simple. Like binary number 1000, right? 100. This is 8, right? This is 8. So this is 2 to the 3rd, which is 8. Because you have 3 bits following that bit. So that is why it's 2 to the 3rd. This bit represents 2 to the 3rd. And this has 16 bits following this guy. So this single one here represents 2 to the 16th. Make sense? So if I want to write this down here for the whole, for this number, like 1 and all zeros, I can use the hex number to represent it. What is that hex number? It means 0x what? If just the one single one here, but all the rest are zeros, I want to represent as a hex number. So it's going to be 0x what? 1? What?
0, 0, 0.
How many zeros?
3.
So for hex, 10 represents 4 zeros, right? So you have totally 8 zeros. So how many zeros do we need for the hex? 4. So that's going to be the hex number. That's going to be the hex number for this number, 17-bit number, which is 1 here and followed by 16 zeros. Any questions on this? It's recorded. You can always come back to and see if you can understand all the things. And there will be a lot of quizzes on timers. That's a fundamental, super basic for the whole semester. And everything runs on this, okay? You just have to understand this first. What's that?
Is there a difference between this timer and the one we were looking at before?
No, all the timers run the same way. But the control registers has a different name, that's it.
Oh.
And also they have different length, okay? Or width. All right. So this number will be important. Why I'm giving you an example, why I'm putting a 1 here and putting all the zeros over here. Because we are going to use this number a lot. If you look at the code, here you'll see it. Okay? Don't worry, I mean, there are so many things to cover. This is the first thing, at least when you see this number, you know what's happening, okay? But why we are going to talk about this? Why? Okay? So now you see this number. This number is what I just talked about. Okay? All right. And then for one of the questions here. if you look at the oscillation, we need a timer that is able to hold for this period, okay, and then toggle. So we just calculated it is 1/800. That's a period, right? And this divided by 1,000, so we can get the times 1,000, so we can get how many milliseconds, and divided by 2, and that's a half period duration. Am I making any mistake over here? This time is gonna be the millisecond. So what about second? It's gonna be 1/800 times 2, right? That's in second. That's in millisecond. Half period. Again, why do we care about half period? Why?
That tells us when to toggle.
You toggle. This is until something happens. We want to do something, right? So before that, we are not doing anything. Until that happens, we do something. We need action. So that's why we need to count until half period. All right. So now this is given, right? And we know that if we don't set up the timer with a different persecutor, I'm going to explain the persecutor really quick. But now let's assuming that 1-to-1 is not changing the counting frequency, which is 16 megahertz. 16 megahertz. That's how fast it's counting. All right. So now we want to figure out the number of counts. Why? Because this is something you have to write into the TCNT1 register to make that happen. Number of counts. We know that this is how fast the microcontroller is counting. Is 16 megahertz counts per second. That's what that means. 16 million counts per second. And we know that this is the time, desired time, to stop counting. Do we need more information to know the number of counts it's going to happen? We know how fast it is counting. And we know how long we want to let it count. Can we know how many counts result from that? Yes. How? Multiplication, right? It's 16 times 10 to the 6. Can I write it this way? Counts per second. Does that work for you guys? Times what?
How many seconds are counted?
Second? What is canceled? Seconds cancel, right? So eventually I'm getting the counts. Okay? It's going to be 16 times 10 to the 6 times make sense? That's the number of counts we are going to need. But so what is that? What is it?
10,000.
10,000? Yeah, because this is 1600, right? 1600. Yes, 10,000. Is 10,000 larger than 2 to the 6? 2 to the 16th? Which is larger?
2 to the 16.
Mm-hmm. So do we have enough room for counter 1?
Yes.
Yes. So how do we do that? So what's happening here for the counter is whenever the timer got started, like timer 1, right? So when the timer, if you start a timer, assuming we know how to start a timer and stop a timer, I'm going to show you what are the code. the lines, start and stop the timer. So now we start the timer. What's going to happen is this guy is going to start counting. So whatever the number this guy's holding will start going up one by one, and that frequency is going to be 60 megahertz until it overflows. And there will be a signal flag will be turned on, okay? So we know if that flag is turned on, then we toggle it, okay? And we toggle it, then we clear the flag, then we can start over. That's how that works, okay? So now this guy can count from 0 to 2 to the 16th, but now we only need a 10,000 counts. How can we do that?
Subtract 10,000.
Subtract 10,000, or assign a starting value of it, so it's not starting from 0, right? Starting from a certain value, and only has 10,000 left, right? Only has 10,000 counts left. So it's going to start from this value and only has 10,000 left. So it's going to only count for 10,000 counts at a 60 megahertz, and then overflows, trigger the flag. Then we toggle, we clear flag. Then the job is done. Any questions on this?
How is the frequency like? How do you get it? Is it something?
Yeah, it's
with
given.
The sound?
Yeah. No. Which frequency? The frequency of the sound?
Yeah. Like
Yeah, the frequency of the sound is. Let me show you. Is here. How many of you know how to play piano? Music, sort of. You don't have to, since I don't know how to play it. But you can at least something. It's something you need to know. It's a really simple concept. Over here, you can see the keys on the keyboard. It has all the keys, the white keys, and also the black keys, right? So it's from left to right. The pitch is going up, which means the frequency is going up. It's getting sharper and sharper, so the frequency is going up, right? So start from C, where is C? Here's C, right? So C, D, E, F, G, A, B. So C, D, E, F, G, A, B, and the black one has a smaller increment of frequency, but from white to white, definitely a bigger frequency difference. It's a higher pitch, stable pitch increment. But anyway, from left to right, it's actually the pitch is going up. Okay, the frequency is going up. From white to black, it's a smaller increment, and so it's like this. From white to black, it's a small increment, and from black to white, it's another small increment. But from white to white, you can imagine it's a bigger gap, bigger increment. So that is why over here it's being marked as A. So all these keys on the keyboard is being labeled as either one of these letters, C, D, E, F, G, A, B, C, D, E, F, G, A, B, right? And a sharp means it's a black key from the previous, like for example, A4, right? A4 is one of the A keys, as a white key, and A sharp is the black one next to it. It's a small increment of the frequency. Any question on this? It's not a music class, but any question on this? Definitely not. I'm not eligible for teaching that anyway. But you know the concept, right? You know pitches and sound and frequencies. Okay, so you can see that from every single one has a certain frequency, and how these are calculated. You use the starting value. For example, it's given A4 is given. Because the keyboard has like 80 something keys, right? So it's repeating C, D, F, G, A, B, C, D, F, G, A, B, C, D. So it could be like C, D, F, G, A, B 1, C, D, F, G, A, B 2, and if you see here 4 is C, D, E, F, G, A, B 4, right? So A4 over here. So A4 and A4 sharp. So A4 is given, which is 440 hertz, and you can calculate A4 sharp using this equation. It's given. If you look at the spreadsheet over here, I showed you how to calculate it. It's actually the previous one times the power of 1.059 or something. It's given. And you do that calculation and then you just drag it. And so you can get all these frequencies in the table. Questions? No, it's very simple. It's just a very simple Excel sheet, okay? And then you can calculate the period from the frequency. After the frequency is done, it's calculated, you can get the period easily by using 1 over it, right? And then half period, just 50% of this period. And if you know this half period, which is the duration you know, and you know how fast it's counting, which is 60 megahertz, so you can get all the counts for the timer, okay? All right. Answer the question, show me, right? So I was at here. To achieve that accurate duration, you give a offset to that timer, TCNT1. It starts counting. For example, I'm just using a bar to show you where the count is, right? So for example, this is a count offset you put in here, and this is 10K counts, right? It's 10K counts. You put an offset here first, and then you only have 10K counts left. So the way to do that is you have TCNT1 0x10000, which is the total counts, the total width. You minus what? Minus the desired count, which is 10K. We'll make it very simple because this is what you need. You got this from the spreadsheet. This is the desired number of counts, and this is the maximum width. You know, because you know this is 16 bits, and you have this one minus this one. It's giving you this offset. All right, so you assign this offset to the counter, so it has something to start with. So start counting from here, and then just need to finish the rest, the 10K counts, which is exactly 800 hertz, or whatever the time, the half period time, with that certain frequency. Any question on this? So every time you start a timer, you give a start value immediately. Okay. Now let's come back to the code. So these are the half period counts for different nodes. You heard that from the demo video, right? Don't. So all these nodes are these ones, different counts, right? Different counts is giving you different frequency. And see how that works? The first one, TCCR1A. Remember, we just looked at TCCR1B, right? So TCCR1A is another register. I didn't have a snapshot on my website in the tutorial. But the thing you need to know is it's another control register. We just need to give a 0 to it, so it's running at the normal mode. There are 7 different modes you can run the timer at, but now just simply give a 0, it's running at the normal mode. And then TCCR1B, you give a 0 to it, you stop the timer. Start the timer first, because this is a setup function, right? So when you are doing setup, stop it first. So it's ready to run the timer in the loop function. And directly give that counts to the counting register. Does it matter if I give it early or later here? If I give it early, if I don't start the timer, which is fine. It's just holding that value there. Whenever it gets started, it will already have that offset value in there, but only has 10K counts left. Okay. Then get into the loop function. See the top button. The top button. This module is not using the timer. It's just a microsecond time delay function. So whenever the top button is low, I press it. If it's low, it's getting into it. If it's still low, which means I'm holding it because my finger is kind of slow, I push on it and still holding it, still detecting a low, and then followed by a curly bracket, and directly using this one, it's a microsecond delay function. So the top button, you press the top button, it's creating all these sound. It's not using the timer, it's using a microsecond delay function you created from tutorial 1. And how that is calculated? See the counts. Here's the counts, right? And divided by 16 mega, even though it's a 16 here, but it divided by 16 mega, and then times 1 million to convert it to microseconds. How this works? Counts is given. So now we need a time, right? So counts. This is given. This is also given. It's asking for time. How to do that? 10K counts. "16 megahertz means 16 mega counts per second. Right? This is given, this is given. We know it's counting at this kind of speed. And we know this is the number of counts we need. How long it takes to finish this number of counts by this speed, by using this speed. It's 10K counts divided by 16 mega counts per second. Okay? Division. So you are getting 10K counts times seconds 16 mega counts. This is getting cancelled, right? So eventually you are getting 10K over 16 mega seconds. If you want to convert it to microseconds, you need to use this number times 10 to the 6. And because this is mega, this 10 to the 6 is getting cancelled. That's why it only has 16 left. So if you come back to the code here, it's only 16 left. Right? Have this number of counts, and you have 16 left. So make a division is directly microsecond delay. And then after that microsecond delay, you toggle the pin, and then you move to the next node. So it's basically using a reminder. The total you have 7 elements, 7 nodes in this list. So it's cycling from 0 to 7 and then 8. Whenever it reaches 8, it goes back to 0. And that is why you are using this, okay? So for example, 7, whenever it reaches 7 plus 1, which is 8, 8 divided by 7 for the remainder, which is giving you 1. So it starts over from 1. Why is not 0? We probably don't need this 1 here. Yeah, but there are multiple ways to do it. Okay, this is just one of the ways. Just trying to cycle it back whenever it overflows. Hopefully this is not giving you a hard time, because this is not the main part of it. All right, but so this is a microsecond delay one, and the bottom button is using a timer. The bottom button is using a timer. So here's a critical thing we need to know. We look at this one. So this part of the code will answer all these questions. Pay attention to it. We probably cannot finish all the questions here. I'm trying to be too ambitious to cover everything. So we'll cover more on Wednesday. Make sure you guys know how to handle timers, okay? So turn this in on Wednesday. So here. The important part. So first, the bottom button is pressed, okay? While this is still being pressed, I'm doing this. What is this guy doing? This is Arduino specific type of code. It's really confusing. But whenever you see this in the future, I hope you guys know what's going on here. So it's basically CS10 is a CS is a timer 1, but bit 0. If you look at the register map here, all the CS, these are the lower 3 bits of the TCC-R1B register. Definitely it has other bits for other controls, but if you look at the lower bits of the TCC-R1B register, these are the 3 bits, okay? CS12, CS11, CS10. So the first one, the CS first one here, CS10. So 0 means the 0 bit. 1 is timer 1. Here, CS, timer 1, bit 1. CS, timer 1, bit 2. So these are the 3 bits. Okay? The one here in the middle means the timer 1. And the lower number here means the location of the bit. So these 3 bits are being used to define the prescaler, and the prescaler is used for slowing down the 60 megahertz clock. You can see here, if I set it up as these lower 3 bits as 000, I'm not doing any, I'm turning the timer off. It's not doing anything. If I set up 001, no prescaling, which means I'm running at the counts, the counting speed is exactly 60 megahertz. If I do 010, it's giving you a 60 megahertz divided by 8. It's slowing that down by 8 times, and so on and so forth. So why do we need to slow it down? I mean, for playing music, it's still useful to play it at a high frequency, but sometimes think about that. If we want to have a timer for like 1 second, you can overflow the 2 to the 16-bit count register easily and quickly. So by slowing it down, you can have a longer duration of the timing. You want to count it slower, okay? And whenever the timer is up, this is the flag. It's the timer overflow flag, timer 1, and this will be set. It becomes 1 whenever the timer is up, and this bit is the lower LSB of this register. Is the timer interrupt flag register 1, and this is the low LSB of this register. Let's take a look. This guy. All right, so we were talking about when timer's up, what's going to happen? There's a flag, right? So flag. So this little flag, timer overflow flag for timer 1 is actually the LSB of this timer interrupt flag register 1 of that register. So this guy will become 1, will be set whenever the timer's up. So we need to clean it. We need to clear this bit, and then restart the timer. That's how that works. So on Wednesday we will do this again and make sure you guys can finish the in-class exercise, and then we can start talking about the lab. So tutorial 2 is due next Wednesday, not Monday. Okay, we'll make it easier. And also for other people who are not getting your board functioning, make sure you work with me today or tomorrow. Get it done. Okay. All right.
What time? Today?
What time? I mean, I'll be here all day.
Okay.
So the senior son meeting probably ends at 5
Okay.
or something, and then I will have some food and then I'll come back.
Okay.
Okay. I'll just meet you guys in 610. All right. So this evening and tomorrow evening. I'll just find you guys over there.
So when